Web and C++ are not an iconic couple. My name is Lukas, and I work as full-stack software engineer at PPRO. Today, we try to understand why C++ fits into a modern web service. How did C++ never find widespread adoption in the networking segment, a market dominated by C? Both Node.js and Python essentially implement the networking stack with C. Network applications being prone to malicious input makes this particularly ironic given C's security track record. The vast majority of today's security breaches boil down to someone blindly calling memcopy. The days where such thing was purely a stylistic faux pas are truly gone. Today, these kinds of bugs have an ever-increasing impact on real people's lives. We all know modern C++ tries to address many of those historic shortcomings. Surely, this translates into applications. If you got questions, just raise your arm. First, we try to see where C++ application makes sense. Then, a quick look at the client side of a web application. And finally, we'll compare implementing an example service using popular C++ libraries. I'll assume that you have some knowledge about networking applications. And of course, this talk is no definite answer. It's merely subjective observations. If all you want to do is serve static content, then those 5 lines of Python will most likely be enough. Import HTTP server from the standard library, create a socket server listening on a port, and start the event loop. Hosting something like a blog does not need to be complicated. In this talk, I want to focus on web services, quoting W3C. A web service is a software system designed to support interoperable machine-to-machine interaction over a network. What makes web services so popular? The service is just one click away. Basically, everyone can use it. The tools to interact with your application are installed and widely used on the vast majority of today's consumer platforms. That leads us into web development. I want to take some time and talk about the advantages and challenges of modern web development coming from a C++ background. Let's talk about the advantages. Feature-rich ecosystem with NPM at its backbone. A wide variety of tools, coming from the assemble-it-yourself world that is C++ tooling, the feeling of just writing the word debugger in your code, and that followed by a sane and intuitive debugging experience inside your browser is a welcome breath of fresh air after years of fighting tools to achieve seemingly simple goals. And all that without having to install anything special. Frameworks, React, Angular, you name it. There's so many that even sites like To-Do MVC exist. Okay, challenges. Given a system that was never intended to be used in today's manner, and even less at such scale, no matter what you do, at the end of the day, your toolchain will be spitting out JavaScript. That leads to a lack of interoperability with older languages and tools. However, that might be a completely different story once WebAssembly gets DOM bindings. The never-ending story of browser support. This brings us to the development cycle. After editing your source files, you compile to JavaScript. You compile to a JavaScript of a target ECMAScript version and plain CSS. The S version usually dictates browser support. However, even older browsers can support modern features with the help of polyfills. Polyfills try to emulate missing language or library features. Usually, they first check if there's native support and then use the appropriate version. With JavaScript, you have the unique problem. You need to send source code over a resource-constrained channel. So there's a notable advantage of shorter variable names and no white space. Of course, we don't want to write source code where all variables have single character names. Okay, now comes the step where we use a tool to uglify our code. The name says it all, it makes our code more ugly. Popular choice is uglify.js, a parser with the goal to produce the shortest possible JavaScript whilst retaining the same logic. On their GitHub page, they have an example where the original file is 450 kilobytes and turns into 220 kilobytes, with mangling enabled. Gzipped, the original is 109 kilobytes, and the minified version only takes up 73 kilobytes. And finally, we bundle the produced files. This comes down to application preference. Some people like single-page applications. They bundle all their logic into a single file, often called main.js. With this approach, we can quickly interact with the application, as navigating to a different section does not require fetching new source code. However, this quickly leads to bloated websites with a horrendous first load experience. The average website these days sends you more bytes source code than you'd need for the entire Doom binary. Another approach is to split up your application into a set of sections and bundle only the code required for each section. That can help to drastically reduce the average bandwidth usage. To give you a practical showcase of the technology we'll be talking about, let us create a small example service. I want to focus on two major requirements. Persistence. User interaction will have lasting changes. Otherwise, you could just ship a client-only solution, which could be much easier and we'd save server costs. Bidirectional communication. You want to keep the user up to date without requiring him to proactively request new information. Okay, now comes the moment where you have to make a leap of faith, to trust me, to visit this non-HTTP address. Okay, anyone feels like doing it? Okay, also go there so that we can take a quick look. There we go. As you can see, it's a small straw poll service. And to stay impartial, I'll vote for turnip, but I'll... Okay, that's unlucky. Okay, I'm not sure what happened there. Probably, like, let me reload it, see what happens. Okay, so, okay. Now can some of you go there and try to vote, please? You can see, should update automatically. Okay, there we go.
Everyone's got the same IP. Yeah.
That's okay. There we go. Okay, maybe one more vote and then we'll continue. Okay, so I think you get the idea. People can vote and we directly see what happens. We don't have to like, this site does not fetch new information. It's the server sending information and the site reacting to. Okay, let's go back to presentation. Okay. Persistence is easy as soon as you have a server. Bidirectional communication is a little trickier. Who of you has heard about WebSockets before? Okay, so like half of the audience, nice. And how many of you have used them in applications before? Okay, so like that's like 10% or so now. For those new to WebSockets, they are a thin wrapper around TCP introduced by HTML5. Of course, we don't want to reinvent the wheel ourselves. We'll use a WebSocket library. Rather than using one library, I want to compare three popular open source choices: Beast, WebSockets, and IncludeOS. We'll compare their interfaces, the code needed for example servers, attack vectors, and of course, performance. The three main requirements are a request handler. Each user request should trigger a call to our function. We want to send a message back to the client WebSocket. And finally, we want to broadcast a message to all open WebSocket connections. Let us start with a batteries included library, WebSockets. It directly provides support for our three requirements. The setup is easy and straightforward. We construct a hub, attach a request handler, bind to a port, and start the event loop. Each time a user sends a message, our request handler is called with the WebSocket itself, a pointer to the message buffer plus its size, and the message opcode, usually text or binary. Before we continue, we have to talk about serialization. Both the client and server need some kind of shared language. Of course, we could use JSON. That would lend itself very nicely in the front end. JavaScript objects are basically JSON objects. However, JSON in C++ requires a library, and we lack validation, not to mention performance. That's why I decided to use flatbuffers. Flatbuffers is a schema-based serialization library. And what makes flatbuffers great is the virtual lack of deserializing and serializing. Instead of deserializing the message and constructing an in-memory representation, we offset jump to the place we care about and just read the memory. Compared to JSON, we can be 3 orders of magnitudes faster and less memory hungry. Flatbuffers are usually used with a schema representation. A schema allows for more efficient message encoding and also validation. All this makes for easy out-of-the-box message validation, as you can see here. However, this does not validate application logic. It can tell us if a vote is present or not. It doesn't know whether a vote is in bounds or if the client has voted already. Here you see the entire schema for our user requests. Flatbuffers supports pods, structs, enums, unions, and tables. In this case, all we need is a type enum representing the request type and optionally a vote. Back to you WebSockets. In order to send a message, we need a WebSocket. The message pointer and size, here wrapped with flatbuffer ref, and the opcode. This call is synchronous. That means the function will return once the message was sent. Sending a message to every open WebSocket connection is very similar. Instead of calling send on a WebSocket object, we need the hub. getDefaultGroup returns a group object representing all open connections. Conveniently, this group object provides a method to broadcast messages. The call to broadcast and send share the same signature. Finally, to tie everything together, the request switch. After validation, we switch based on the request type. This works given that request type is an enum. To keep things simpler, we'll not talk about the poll data object for now. Just note it takes care of creating and managing our flatbuffer objects. In case of a poll request, we send back our constant poll object. In case of a result request, which should come with a vote, we try to register the vote and give it 2 callbacks. The first should be triggered if the vote is invalid. The second if the vote was registered successfully. If the vote was registered successfully, in our case, we want to broadcast the updated vote array. Otherwise, we send an error stating an unrecognized request type. Of course, we need a client. In our case, a static web application. The 2 requirements we have for our client are WebSocket support, technically not part of any ECMAScript version yet, however, it has been implemented in nearly every browser by now, giving us 93% of the global web browser users. And we need support for our choice of serialization language. Flatbuffers currently ships with bindings for 8 languages, including JavaScript. Okay, again, we'll take a look at the setup. First, we create a new WebSocket, set its binary type to array buffer, and then add our event listeners. A WebSocket connection usually has 3 event types. Open, the request triggered once the HTTP request, upgrade, and handshake were successful. Message, the event triggered each time the server sends a message. And close, the event triggered by either the server sending a close frame or a failed ping-pong request. Again, we switch based on an enum, this time with the response type. There are 3 known response types: poll, result, and error. Unless there's an error, we just trigger the relevant object update. Okay, join me on a short expedition to the land of JSON. What? Let's take a look at a highly complex task of sorting an array containing numbers. Okay, what does options contain now? Anyone willing to guess? 1, 2, 10, and then? 21. Okay. No, turns out it's 1, 10, 2, and 21. Okay, so. Yep. Obviously, sort treats numbers as strings and then compares them based on the Unicode points. Okay, let's give it a lambda. We want to sort, right? Like this looks very similar to C++. We just tell it, okay, please sort based on this on those rules. Okay, so what does it look like now? No, it's either of those two, depending on your browser implementation. Okay, the standard sort expects a comparison function to return either a positive or negative number indicating larger or smaller. So what we need to do is subtract the numbers from each other. That'll do the trick. Yeah. Okay, of course, this has historical reasons. Like if the people that are in charge of today's standards would get to design this again, I'm pretty sure they wouldn't do this, but like, okay. You thought C++ implicit conversions are bad? Yeah, okay, so what does this valid piece of JS evaluate to? give me a minute, okay. 42? No. Well, let's find out, right? Okay, let's copy. We're inside a browser, so we can open the console. The string, it's fine. No, it's not really. Okay. Turns out you can express the entirety of JavaScript with just 6 symbols. Okay, back to the occasionally less insane land of C++. Let us take a look at our second high-level WebSocket library. However, include-as is much more than a WebSocket library. Who went to Alfred's talk earlier this week? Okay, so there's a couple of you. For those unfamiliar with include-as, it's a young unikernel project which allows you to create applications that are compiled into bootable special-purpose operating systems. All the relevant pieces of the OS are statically linked into your application. The result can be a bootable image with networking stack with a size in the area of a megabyte that boots in milliseconds. Onto why someone would want this later. First, we include the relevant OS components, retrieve a reference to the OS internal network stack, attach our request handler, and bind to our port. And again, start the event loop. This time, we have to trigger the HTTP upgrade ourselves. We try to upgrade if the request is both GET and comes from a WebSocket address. I'm not entirely sure this is 100 like RFC compliant. I just saw it on in their example. Might be that there's some edge cases where this is wrong. Our request handler will only be triggered each time a connection is established. So we still need an event handler for the client messages. This is what a simple echo server could look like. For those of you thinking they're having a déjà vu, yes, sending looks very similar to WebSocket's interface. Again, we write a pointer, size, and opcode. Include-as does not have native broadcast support. We learn how to implement that once we look at the Beast example. Part of the upcoming Boost versions, Beast is by far the lowest level library of the 3. Setting up a Beast server seems harmless enough. A couple of includes, creating an I/O service, subscribing our events, and starting the event loop. Let's look at listener, implemented by us. Before we do that, let's first revisit event loops. To recap the event loop model, we take a quick look at a synchronous beast example. In our top level loop, each time we create a new TCP socket. Accept should block until we get a connection. Once we have a new session, we spawn a worker thread and transfer ownership of the socket. And you can see it's an endless loop. First, we construct the WebSocket stream by moving in the socket. Then we block until the handshake was resolved. Again, we go into an endless loop. The read function should block until we receive a client message. Here we just echo back the message. Of course, we want to take advantage of ASIO's async interface. For those of you unfamiliar with the concept of async I/O, the core idea is, rather than blocking until an I/O event is done, to start the operation and to query the result state. Usually, this means that synchronization bubbles up to some kind of event loop. We need some kind of loop that resumes at arbitrary points. Neither for or while are going to cut it. What can a loop be reduced down to? Switch? Oh, more low level. Yes, go-tos, there we go. Okay, only problem, as children, we've all been told about the story of the big bad go-to, so maybe there's a better way of doing this. Using a cyclical call graph. You can see bar calls foo and foo calls bar. This has the advantage that we can suspend our loop at arbitrary points and give back control to the parent, which then can resume it at a later time. With that, let's take a look at the actual beast example. Of course, to keep things manageable, there's a lot of code missing. Constructing listener starts the event loop. Async accept takes a socket reference to move into and the continuation handler. Strand is an executor. Okay. This creates a new session. Note that onAccept always calls doAccept, which in turn calls onAccept. Anyone sees a loop? Okay. Okay, so let's take a look at, we have something that responds to all the incoming connections, but we still need a session loop. That's what we did earlier by spawning a thread and telling it to loop endless again. So this is the entry point for our session. And it should look familiar. It's basically the same as the listener constructor. It kickstarts the session event loop. The session event loop is more elaborate. So I split it up into 3 core components, this being the start. Here, the reading part of our event loop. After clearing our target buffer, we subscribe a read operation. Once the read is completed, our handler should be called. In this case, onRead. Note that async, beast, and ASIO use the much faster error code pattern instead of exceptions. Because in the synchronous example, there was an endless loop, and how do we exit that? Of course, exceptions. Writing looks very similar. One thing to note, beast expects to write a range of buffers. However, they will not be represented as individual messages. The purpose is to avoid copying buffers if possible. Okay, all this might seem a little overwhelming. Let's recap the session event chain. onAccept calls doRead, which in turn calls onRead, which calls doWrite, which calls onWrite, and that calls doRead again. And you can see this closes the loop. Yeah.
Stacks. Are you relying on internal caching, or is it just has the call? How can you not just running a stack?
Okay, so the question was, how am I not just growing the stack? Well, the function does not, okay, you saw this strand.wrap, and then you add a function. That's basically how you do the continuation, and that's an executor, right? So you don't, it's not a linear call stack where you just at some point do stack exhaustion. No. It's, there's this element in there, the executor, that takes care of like managing who should call when. And at the end, it bubbles up to the IO service event loop, which then takes care of like, I'll go down this path. At some point, our loop somewhere in there returns. It knows how to continue, but that's the part of someone else to call that function again. Yeah? Okay, earlier I mentioned manual broadcast. We store all our sessions in an unordered map. That way we can quickly add and remove sessions. A broadcast queues a message for all open sessions. Of course, now that we add messages from the outside and sending is async, we have to take care of the case where we want to send a message, but there's a write already in progress. In our application, add message is only called by broadcast, so that we can avoid adding the message if either the client hasn't voted yet or if there is already a write in progress. We assume that every write after a vote is a result response, which should refer to the most up-to-date result. Flush message queue is called both externally and internally. It replaces the position of do write. Conceptually, it starts a write event chain that should deplete our message queue. If this event chain is already in progress, flushing is a no-op. Notice that as soon as we queue a write operation with async write, we set our internal state to write in progress. Let's look at the after write callback triggered by the write operation. First, it releases our conceptual lock and then calls on write, which depending on the queue size calls either flush message queue again or do read. Similar story for reading. I abbreviated the async read call, but conceptually after read is the same as after write. For this model to work, it's imperative that we avoid fragmenting our event loop. For each session, there should only ever be one chain of events. The whole chain forms one big loop, and at the same time, some of its segments may temporarily form a smaller loop with each other. However, given enough time, it should always unfold to our overall session event loop. Ideally, having built an infinite loop, there's a way to exit it. Having completed a read, it can set the error code to WebSocket error closed. In this case, we call listener and erase the session with our associated ID, essentially destructing ourselves. Things like the error responses or the poll response are created once. Given that our poll data object is owned by listener, we guarantee a pointer lifetime for those objects that is the same as the lifetime of the server. Using a synchronous interface avoids many pitfalls. Before sending an object, we serialize it, then send, and the send call blocks until the send happened. And we destruct our object via write. With async interfaces, this gets trickier. We have to guarantee a lifetime until all write operations are done. Okay, shared lifetime. Many would now suggest using a shared pointer. Yes, that would work. I believe we can do better. Let's see how we can avoid heap allocation. The only dynamic response in our application is the result response. New votes update the vote array. However, we know that serializing this object will always create an object of the same size. By copying the new object into the previous location, any of our pointers avoid being invalidated. We avoid heap allocation, and as a result, write will always write the most up-to-date result. That way we can reduce the amount of messages we need to send, saving both bandwidth and local resources. Okay, to give you a quick idea about the effort required to use each library, I ran our example implementations through word count. WebSockets sits at a comfy 1.6 kilobytes. IncludeOS isn't far away with roughly 3 kilobytes. And Beast, however, being a lower level library, results in 9 kilobytes of source code that we had to write.
How many lines of code is that?
Okay, the question was how many lines of code is that? I think the WebSockets one is less than 100, and for Beast it's more than 400. Okay? Let us now compare a big productivity factor, the incremental compile time. Note, the results are the 90th percentile compiled with Clang 4. WebSockets is linked as a static library, making it a breeze to work with. I couldn't get IncludeOS to build as debug, so I measured the default settings, with 90% being under 3 seconds. Still nice to quickly iterate with. Well, Beast, being part of Boost, carries the burden of the template-heavy header-only approach, right? So, in terms of documentation, WebSockets barely has any. It's a little better for IncludeOS. Still, you'll find yourself reading source code most of the time. Beast, on the other hand, has excellent documentation. To keep the examples smaller and simpler, all of our examples were purely single-threaded. That gives me little experience in this context. However, Beast has clearly been designed with multi-threading in mind. Still very complicated and easy to get wrong. Not sure about WebSockets. I've read conflicting reports, like people claiming it's amazing, people claiming it's like breaks all the time. And IncludeOS currently does not support any kind of threading. Both WebSockets and Beast have native support for SSL via OpenSSL. However, it should be easy to put an IncludeOS application behind a reverse proxy like Nginx. That then takes care of the SSL. Looking at possible attack vectors, both Beast and WebSockets are regular binaries, allowing for a wide variety of exploits paired with a mature set of tools for reverse engineering. IncludeOS's unique execution environment makes that harder. What IncludeOS can't protect you from is application flaws. Let's say there's a bug in our registration code. That way, someone could perform vote manipulation. A unikernel is not going to protect you from that. What it can do is limit damage of things like remote code execution. Many exploits rely on finding libc and then using it to spawn a shell. It can mitigate a set of known exploit propagations, like the aforementioned system call. Remember, the biggest attack vector is and remains social engineering. Okay, this is my first time benchmarking a network application. Please take my results with a bucket of salt. Again, results are the 90th percentile from running WebSockets scalability test locally. Unfortunately, I didn't manage to benchmark IncludeOS. I ran the benchmark in 2 settings. First, with 100 concurrent connections. No big difference in terms of user space memory usage, both sitting at around 4 megabytes. Onto the connections per millisecond. At this small sample size, this shouldn't be all that representative. now with 10,000 concurrent connections. With its extremely special purpose implementation, WebSockets manages to have an impressively small memory footprint, using only an additional 2 megabytes for 10,000 concurrent connections. At that rate, you can host Google-esque traffic with less RAM than your phone. Beast does well enough. At this timescale, your application is much more likely to become the bottleneck. This laptop managed to request and serve 10,000 connections in a third of a second. With that kind of traffic, you should be able to afford better hardware, for sure. So, who's the winner? Which library is the best? Wrong question. 3 libraries I presented all aim to achieve vastly different goals. The better question is, what do you want? To summarize, I'll associate each library with a key strength. If you want an easy, fast, and lightweight solution, take a look at WebSockets. Albeit being a young project, IncludeOS shows promising progress towards being a solid choice for security-oriented services. With its aim to be as modular and adaptable as possible, Beast comes with an inherent complexity and trade-offs. Given its aspiration to become part of the standard library, it could very well be core of many. It could very well be core of many upcoming libraries. C++ is seldom the best at anything. Python has a more convenient syntax. C reliably beats us in the computer language benchmarks game. Rust has better type checking. Elixir has more convenient multi-threading. And all the new languages have a central package manager, facilitating a shared ecosystem. So, what's C++'s niche? Libraries like WebSockets show there can be a nice batteries included experience yielding outstanding performance and efficiency, fulfilling the long-standing promise of safe, high-level constructs compiled down to efficient low-level components. Paired with static type checking, no need for a runtime, and mature compilers and tools, that's a sweet spot of versatility no other language hits. Of course, C++ does not stand still. Let us look at existing issues and how they might be solved in the future. Most glaringly, the complete lack of networking in the standard library, addressed by the networking TS. Lack of execution control, addressed by the executors TS. And a lack of suspendable functions, addressed by the coroutines TS. Also, a lack of Unicode support, but there are a couple of papers, but there does not seem to be a unified vision so far. You'll find the source code for both the presentation and example here. If you're watching this video and you want to tell me how wrong I was, here you go. Okay, let's take a quick look at the vote result again. Maybe some of you voted by now. Okay, I'll leave this up. So who won? Never. Okay, so we're all hardcore fans, I see. Well, you can vote. The address is down there. Like, it's not particularly hard. Just pull out your phone. Okay. Okay, any remaining questions?
Does IncludeOS not supporting threading now, is that not a huge stopper, or do you just do everything in a single event loop on a single thread?
Can you repeat the question, please?
You said IncludeOS does not support any threading. Is that not a huge stopper, or do you just do everything in an event loop in a single thread?
Okay, to be honest, I think until you reach the limits, like it's fairly lightweight, right? You don't do context switching in there, and everything is basically like delegates calling each other. Yes, at some point you'll reach a limit, right? But I'm betting there's like maybe 2 handfuls of companies on this world that actually reach this kind of traffic. You can easily handle something like 10, 20,000 connections at a time with still a single-threaded approach. But they have a plan to add support for it. There's a talk at Meeting C++ this year where you talk about it.
You mentioned flat buffers. Does flat buffers make any guarantees about binary compatibility between releases of flat buffers?
Oh, okay. So the question is if there are binary compatibility guarantees made between releases. Okay, I'm not sure, to be honest. I know it has, like, they know about these kinds of issues, and I think the answer is yes, because each field is optional. For example, in a table, each field is optional, and if you just add ones, you can even tag old ones with deprecated, but I think they guarantee the same layout. But I'm not sure between versions. It's still a fairly young project.
Yeah, so it means if you upgrade from, I think, version 1.4 to 1.7, something like that, that they guarantee that you can mix versions on different platforms.
I believe so, yes, but please look it up. Okay, I think that wraps it up. Thanks.